Today we're going to talk more about equivalence relations and equivalence classes. So the last time we talked about relations and equivalence relations. So remember that a relation on a set is nothing more in our definition than a subset of A cross A, or A times A. And we say that X is related to Y if the pair XY is in this set R. And an equivalence relation is just a relation which satisfies three properties. The property of being reflexive, the property of being symmetric, and the property of being transitive. So reflexive says that any X in A is related to itself, that if X is related to Y, then Y is related to X. And if X and Y are related and Y and Z are related, then X and Z must be related. So these logical statements have to be true for all X, Y, Z in the set A. All right, so we looked at some examples last time of equivalence relations, some familiar ones, and especially we looked at an example on a small set, a set of cardinality 4. We looked at a bunch of examples of equivalence relations there. We also proved that the notion of equivalence mod n is an equivalence relation. So an equivalence relation, so the way you could kind of think about it or conceptualize it is that it's an abstraction of the idea of equality. So we take the most important parts of our notion of equality and use them as the basis of the definition for equivalence relation. So if you have an equivalence relation R, X is related to Y basically means, the way you can think about that, is that with respect to the property R, you can't tell the difference between X and Y. So even though X and Y are different elements of this set A, once you include this equivalence relation, the equivalence relation can't tell the difference between X and Y. So there's some appropriate degree of sameness to X and Y as measured by R, so that they should be considered to be equal. All right, so that's kind of the way you can think about that, is that R introduces some measure of sameness or difference between the elements. So if X is related to Y, they're considered sufficiently the same that they should be considered equal with respect to this property R. So an example you might think of, a familiar one from high school geometry, is the idea of similar triangles. So triangles are similar basically means that you can take, so two triangles are similar means that you can take one of the triangles and scale it and translate it and rotate it and fit it on top of another triangle. So in this red circle here, I have some equilateral triangles of various sizes and situated in various orientations, and you can take those triangles and scale them and rotate them to make them fit on top of each other. And in the blue circle, I have some isosceles triangles, and in the green circle I have some scalene triangles that are similar. So this notion of similarity says that, well, even if you have one equilateral triangle that's big and another one that's small, in some sense these are sufficiently the same that you should sort of ignore the difference between them that comes from the size and just sort of focus on the overall shape of the triangle, the overall inclination of the sides to each other, and use that as your measure of sameness of the triangles. So similarity introduces this looser notion of equality between triangles that is still quite useful in practice, as you've no doubt seen in the past. The main example that we're going to work with when it comes to equivalence relations is equivalence mod a natural number. So in particular, let's look at equivalence mod 4, and then we'll look at the general case and see what this indicates to us about equivalence relations. So we're we're going to look at these examples, and then we're going to try to generalize what we've learned from the examples to say something that's applicable to any equivalence relation. So let's just start by recalling that A and B are equivalent mod 4. That means that 4 divides A minus B, right? Okay, so let's start just by looking at 0. Right, so the integer 0. And so of course 0 is related to itself. So I'm going to start drawing a picture of the equivalence relation, equivalent mod 4, on the integers. Right, so 0, that's equivalent to itself. Right, so there should be an arrow pointing from 0 to itself. Okay, what are some other integers that are equivalent to 0? So 4 is equivalent to 0, mod 4, right? Because 4 minus 0 is 4, and that's divisible by 4. So if I label 4 here, you see that there's got to be an arrow pointing from 0 to 4, right? Because, right, for the reason I said. And also because we have an equivalence relation, it's symmetric, so we have to have that single-sided arrow has to be a double pointed arrow. Okay, and so what other things are related to 0 mod 4? Well, and so A is equivalent to 0 mod 4. That's if and only if A minus 0 is divisible by 4, right? So if and only if 4 divides A. Right, so every multiple of 4 is going to be related to 0, right? So if I put other multiples of 4 in here, negative 4, negative 8, etc., then we have to have arrows from 0 to all of those things, right? And then any of those arrows has to be a double arrow because our relation is symmetric. So we start getting a very busy looking diagram already. Right, so all of the multiples of 4 are related to 0 mod 4. And now because our equivalence relation is transitive, right, so if I take any one of these, so let's see if I look at, so I look at say 8 here, so I'm just picking 2 at random, 8 and negative 4. Well, 8 is connected to 0, right? There's an arrow between 8 and 0 because there's an arrow between 0 and any one of these things, right? So there's an arrow between 0 and 8, and there's also an arrow between 0 and negative 4. Right? So in other words, so we have 8 is related to 0 mod 4, and negative 4 is related to 0 mod 4. Right, but since we can get from 8 to 0 and from 0 to negative 4, we should be able to get to from 8 to negative 4 directly, right, which we can see formally from this pair of things here, because, for example, you can switch the negative 4 and the 0, right? So I can replace this here with 0 is equivalent to 4. Negative 4 mod 4. And then because the zeros match here, right, by the transitivity, that implies that 8 is equivalent to negative 4 mod 4. And so there must also be an arrow connecting 8 to negative 4, and thereby the reverse arrow as well. Right, so what we've found is that so every multiple of 4 is connected to 0, right? But then any two things which are connected to 0 must be connected to each other. So all of the multiples of 4 are connected together to each other, right? So there must be so not only is there something connecting 8 to negative 4, there must also be something connecting 8 and 4, and 8 and negative 8. And there's got to be something connecting 4 and negative 4, and 4 and negative 8 and 8 and negative 4. Right? I think that's all of the ones. And then, of course, every other multiple of 4 as well. So there's, so negative 12 out here, that's also connected to negative 8 and to negative 4 and to 0 and to 4 and to 8. Right, and so very quickly this diagram gets way busier than it's worth. Okay, so what we saw is that every multiple of 4 is connected to 0, and therefore any two multiples of 4 are connected. Okay, we could also do something similar starting with 1. So if we started with 1, you'd have to have an arrow at 1, and then a is equivalent to 1 mod 4. That just means that a minus 1 is divisible by 4. Right? So in other words, a is 1 more than a multiple of 4. All right, so we would have to have, so 5 is 1 more than a multiple of 4, and 9 is 1 more than a multiple of 4, and 13 is 1 more than a multiple of 4, and let's see, negative 3 is 1 more than negative 4, which is a multiple of 4, and negative 7 is 1 more than negative 8, which is a multiple of 4, and etc. Right, so each of these must be connected to 1, and therefore we have double arrows. And then the same reasoning as above, any of these ones that are connected to 1, right, any two of them are connected to 1, so any two of them must be connected by the transitivity, right? So there must be not only all those arrows, but like negative 3 and 5 have to be connected, and negative 3 and 9 have to be connected, and 7 and 13, and all of the possible combinations here. And so there's a whole bunch of arrows I didn't even, right? So you got these have to be connected, and those have to be connected, and yeah, so gets too busy to even fill in all of them pretty quickly. Okay, so again, every number which exceeds a multiple of 4 by 1 is connected to 1, and therefore any two such are connected. Right, and you can repeat this story with 2 and with 3 as well. So basically what we observe is that our equivalence relation, so equivalence mod 4, creates 4 different classes of integer. And so the first one, that's this first picture up here with starting with 0. So how we got that is that it was all of the integers which were connected to 0, right? So that a was equivalent to 0 mod 4. Right? And then we had, in the second one, all of the integers which were connected to 1 mod 4. And we could have proceeded on to 2 and 3. And we don't have to go any further because all of the integers that are connected to, so we looked at all the integers that were connected to 4 mod 4. Well, if any integer is connected to 4 mod 4, right, is equivalent to 4 mod 4. Well, 4 is equivalent to 0 mod 4, right? So any integer which was equivalent to 4 mod 4, right? So imagine, so if you're equivalent to 4 mod 4, it'd have to be some integer, right? You'd be connected by an arrow coming into 4 like this. But then you could follow this arrow here that connects 4 to 0, and then that would mean that whatever this integer was that was connected to 4 has to be connected to 0 as well, right? So it would have to actually be in this first set here. So we would just, so if we tried to look at all of the A in Z that were equivalent to 4 mod 4, we would just arrive back at our first set here. Okay, so these are the 4 different classes that that equivalence mod 4 breaks the integers up into. And so we can label this first class, we'll label this the equivalence class of 0. So this is the equivalence class of 0. This is the equivalence class of 1, equivalence class of 1, and then the equivalence class of 2 and 3. Right, so this would be equivalence class of 2 and the equivalence class of 3. Oh, and then down here, we could also consider this set, the equivalence class of 4, right? So it's everything that's connected to this 4 mod 4. And as I briefly argued, that should be equal to the equivalence class of 0. And so equivalence class of 4. And so this could go on, etc. But the basic, as you see from the, can sort of see from the picture, the basic claim is that these 4 sets here are going to already exhaust all of the integers. So considering any other equivalence classes like 4 and the equivalence class of 4 and the equivalence class of 5, those are going to be redundant. Right? So there are redundancies. So the equivalence class of 0, that's the same as the equivalence class of 4 and the equivalence class of 8, etc. And this, so we're going to prove all of this stuff rigorously so that there's no doubt about it. But it should be sort of intuitively clear from the pictures at the moment. So that's what I'm going on at the moment. So the equivalence class of 1, that's the same as the equivalence class of 5, right, or of -3, right, etc. And then 2 and -2 and 6, right, they all differ by some multiple of 4, and 3 and -1 and 7, etc. So let's set this up now in some generality. So definition: if n greater than 1 is a natural number and k is some integer, then the equivalence class of k, equivalence class of k modulo n, is the set. It's denoted by k in square brackets like above. And it's all the integers which are equivalent to k mod n. So it's all of the a such that a is equivalent to k mod n. Okay, so it's in terms of the equivalence relation diagram, you can, if you think about it in terms of the pictures of equivalence relations, it's like any of the a such that there's an arrow pointing from a to k. Right, if you were drawing a picture of the equivalence relation. And so it's all of the a such that there's some arrow pointing from a to k. And in terms of, intuitively, in terms of the integers, an a is in here if you can get to a from k by taking hops of step size n, right? Starting from a, skipping by hops of size n. If you can get to k, then a is in this equivalence class modulo n. Okay, so that's the definition. That just generalizes what we were doing above there. Right, so you can see the equivalence class is 0 up here. That was just all of the a that were equivalent to 0 mod 4. So now we just have, the general equivalence class mod k, or equivalence class of k mod n is all of the a that are equivalent to that fixed k mod n. Okay, so let's prove a little proposition about this. So above, we saw that there was a kind of a redundancy in the labeling. So that's the first thing we're going to do. So we see here that, so we saw in the picture that it seemed intuitively clear that like the equivalence class of 0 is equal to the equivalence class of 4. And that would be the same as the equivalence class of 8. And looking at the other lines here, we see that a general proposition we can formulate is that these equivalence classes are going to be the same exactly when the things inside the equivalence class, so like, so this 1 and 5 and negative 3, what they all have in common is that they're all equivalent mod 4 in that case. So our proposition is that if k and l are equivalent mod n, then they generate the same equivalence class. So the equivalence class of k is equal to the equivalence class of L. And in fact, the converse also holds. So the converse holds also. So here's the proof. So first, suppose, so prove that if k and l are equivalent mod n, then their equivalence classes are the same. So we let, say, a be in the equivalence class of k. And we want to show that a is in the equivalence class of L. Okay, so well, what do we get from a being in the equivalence class of k? Well, by definition, that means that a is equivalent to k mod n, right? The equivalence class of k is everything that's equivalent to k mod n. Thus, then, let's say then a is equivalent to k mod n. Well, we have a is equivalent to k mod n and k is equivalent to L mod n, right? So by transitivity, a is equivalent to L mod n. Okay, and just remember where we're trying to go. We're trying to say that a is in the equivalence class of L. But the equivalence class of L is exactly all the things that are equivalent to L mod n, and we just said that a is equivalent to L mod n. So this means that A is in the equivalence class of L by definition. Okay, so the equivalence class of K is contained in the equivalence class of L. Now suppose that, let's say, B is in the equivalence class of L. Well, as before, then B is equivalent to L mod n. Okay, now so what we want to say is that B is in the equivalence class of K, right? So we want to say that that B is equivalent to K mod n. So we have is B is equivalent to L here, and we have K is equivalent to L there, right? So L, that's our middleman. We have L here, we have L here. So we should be able to say that B is equivalent to K by transitivity. It's just that first we have to use symmetric property. So we have to put the L here, and we have to move that over there. So we have to switch them around. So using K is equivalent to L mod n and symmetry, we have B is equivalent to L mod n and L is equivalent to K mod n. Thus, by transitivity, again, B is equivalent to K mod n. And this exactly means, which exactly means that B is in the equivalence class of K. Okay. So that this shows that the equivalence class of L is contained in the equivalence class of K. So equivalence class of K equals the equivalence class of L. All right. To prove the converse, suppose that the equivalence class of K equals the equivalence class of L. So what we want to show is that K is equivalent to L mod n. So to show K is equivalent to L mod n is equivalent, by definition, to showing that K is in the equivalence class of L. Right? But the equivalence class of A equals the equivalence class of L, and clearly K is in the equivalence class of K by reflexivity. So what does it mean for K to be in the equivalence class of K? It means that K is equivalent to K mod n, since K is equivalent to K mod n. Right? So this completes the proof. So that's the formal proof, but in terms of the picture of an equivalence relation, the diagrammatic picture, this is a fairly simple proposition to kind of see. So maybe the proof is too formal, the statement's too formal to kind of interpret. But basically, if you think about it in terms of the picture, it's very simple to see what it's saying. So you have your K and your L. So K equivalent to L mod N. In terms of the diagram of the relation, there's got to be an arrow from K to L, right? And then the equivalence class of K, that's all of the things that are related to K, right? So that's all the things, right, all of the things that are pointing into K. And the equivalence class of L is all the things that are pointing into L. So the proposition says that if there's an arrow pointing from K to L, then anything that points to K must also point to L. And why is that? Well, if anything points to K, like this dot here, then since K is pointing to L, there must be an arrow from K to from that thing to L as well, right? So there must be this third side here, right? And if anything, on the other hand, is pointing to L, like this point here, that's pointing to L. Well, since there's that arrow from K to L, there must be the arrow going back, right? So we must have this arrow going into L and then follow up the arrow to K, and so there must be this third side by transitivity, right? So this blue thing must also be in the set of things that are pointing to K, right? So that's sort of diagrammatically, diagrammatically that's exactly just what we wrote down in the proof. And on the other hand, if the set of things, so the converse proposition just looks like, and if you have two things, K and L, oops. So if you have K and L, and if you know that the set of things which point to K, so if anything which points to K also points to L, right, and vice versa, anything that points to L also points to K, well, then there has to be an arrow from K to L. And that's because, in particular, K has to point to itself, right? So what we said is that anytime there's an arrow pointing to K, then there also has to be an arrow from that thing pointing to L. So that means there must be an arrow pointing from that to L. So K must be related to L. And so what this emphasizes, the thing to maybe realize about this proof, is that, so note, that's okay. Note this proof doesn't use the definition of equivalence mod N. It only uses the properties. It only uses the reflexive, symmetric, and transitive properties. You can see that. So we hit transitivity there, symmetry, transitivity again, and then we also have reflexivity, and right, yeah, and that's it. So we used all of the properties at least once, and we needed to use all of them in order for the proof to work. Okay, so basically this proposition, eventually we'll see that this holds, that there's a more general version of this proposition that holds for any relation on any set. Okay, so since we only use the reflexive, symmetric, and transitive properties, it should, sort of analogous thing should hold for any relation, because this doesn't depend on the definition of equivalence mod N, it just depends on those abstract properties of equivalence. Another thing that was pretty clear from the pictures above is this proposition. So let n greater than 1 be a natural number, k and l be integers. So what's apparent from the picture above is that our equivalence classes, they were either totally disjoint or they were identical with each other. And so the equivalence class of 0 is like 0, 4, 8, -4, -8, etc., all the multiples of 4. The equivalence class of 1 was all the multiples of was all the numbers which, when you subtract 1, gives you a multiple of 4. Right? So there's no overlap between that and the multiples of 4. And the same thing with the equivalence class of 2. So that would be all of the things which exceed a multiple of 4 by 2. So that's not going to have any overlap with the multiples of 4 or the equivalence class containing 1. And then when we finally did get some overlap, like with the equivalence class of 0 and the equivalence class of 4, when they overlapped, they were exactly equal. So there's like this dichotomy between the equivalence classes. They either overlap completely or they don't overlap at all. And so we can show that that's the case. So we have our natural number, we have our two integers, then the equivalence class of k equals the equivalence class of L, or their intersection is empty. Proof. So, well, if their intersection might be empty. If not, it has something in it, right? So you might as well just suppose that this is not equal to the empty set, and then we'll show that they have to be equal. And so then there's some B, which is in the intersection. So B is in the equivalence class of K, and B is in the equivalence class of L, i.e. B is equivalent to K mod N, and B is equivalent to L mod N. So by symmetry, K is equivalent to B mod N, and then by transitivity, so you have your B here and your B here, that's going to say that K is equivalent to L. Then by transitivity, K is equivalent to L mod N. And so by the previous proposition, the equivalence class of K and the equivalence class of L are equal. So thus, equivalence class of K equals the equivalence class of L by the previous proposition. And that is the whole proof. So basically, the proof is like if you have K here and L here, and then you're looking at all the stuff that is related to K, that points to K, and all the stuff that points to L, they're either totally disjoint like this, or they have something in common. So if they have something in common, blue and yellow makes green, right? So there'd be some green guy which is connected to both K and L. But then if you have that, then L must be a blue arrow. There must be, right, because L must be connected to K, since you can go from L to K along this route here, right? And then you can go from K to L along the opposite route, and so K must be, there must be this yellow arrow here, and yellow and blue is green, right? So there's this double arrow connecting K and L, and once you have that by the previous proposition, the equivalence class of K and the equivalence class of L must be equal. So any of these guys pointing to K must also be pointing to L, and any of these guys pointing to L must also be pointing to K. And so that's basically the proof. And again, it's just by the, so all we used here, so we use symmetry and we use transitivity. So again, that's by just the general properties of equivalence relation, not really the definition of equivalence mod n specifically. So these will essentially, this proposition will be applicable in general to equivalence relations. Okay, so basically in these last two propositions that we've proved, we've shown that if you're looking at equivalence classes of integers, so the equivalence class of K and the equivalence class of L, then those equivalence classes, there's a dichotomy between them. They're either exactly equal or they're completely disjoint. So disjoint just means that their intersection is the empty set. So they either intersect completely or not at all. And so that's the second proposition, and the first proposition tells us exactly when the equality case happens. So it tells you how K and L are related when you have equality. If you have equality of the equivalence classes, that means the K and L must be themselves equivalent, and that's an if and only if. Okay, so what I wrote down here is I just wrote down some examples. So the last thing we're going to say about equivalence modulo and a natural number n is that the equivalence classes that the union of all the equivalence classes is the integers themselves, and there's a particularly simple way to write down all of the possible equivalence classes. So take a look when n equals 3. We have the equivalence class of 0. That's all of the multiples of 3. The equivalence class of 1, that's everything which exceeds a multiple of 3 by 1. You can see you have 1, 4, 7, -2, -5, right, extending in both directions. Just adding 3 as you go to the right, subtracting 3 as you go to the left. And the equivalence class of 2 is everything that exceeds a multiple of 3 by 2. So adding 3 to 2 as you go to the right, you just keep adding 3, and you keep subtracting 3 as you go to the left. And you can see that these three sets, as they should, they don't overlap at all, right? So we know that has to be the case. And also the union is all integers, all of the integers. So any integer you can think of is represented in here. And basically you can convince yourself of that because 0, 1, and 2 are in right. 0 is in the first, 1 is in the second, 2 is in the third, and then all the other numbers we just get by adding or subtracting a certain multiple of 3 to those, right? So if you start with 0, 1, and 2, if you add 3, right, you add 3 to 0, you're going to get the next one here. You add 3 to this, you're going to get the next one here. Add 3 to this, you're going to get the next one there, right? And then you keep adding 3, you're going to just replicate to get the next 3, add 3 to those 3, you get the next 3, right? And so you get everything going this direction, and if you subtract 3 starting from here, then you get the next lowest 3. So you get 0 minus 3, -3, -2, -1, and then just keep subtracting 3. You're going to get everything. Okay, so that's the basic intuition for why you get all of the integers there. As long as you have 0, 1, and 2, you're going to get all of them. And then the same logic applies for n equals 4, right? So if you have 0, 1, 2, and 3, the equivalence classes of those, if you add 4 to 0, 1, 2, 3, you're going to get 4, 5, 6, 7, and then you add 4 to that, you're going to get 8, 9, 10, 11, and you're just going to, as you keep adding 4 to all of those, get all of the positive integers, and if you subtract 4 from those 4, then you're going to get all of the negative ones. There's not going to be any gaps there. So you have these so the union of those sets is equal to all of the integers, and there's no overlap between them. They're all mutually disjoint. Any two of them are disjoint. Okay, so this is the case in general. So here's a proposition. So let n greater than 1 be a natural number. Then every integer is in exactly one of the sets. And so one of the sets 0 ... up through n minus 1. Right, same pattern as above. And so there's n of these sets here. So starting with 0, counting up to n minus 1, there's n of those sets. So another way to say that every integer is in exactly one of them is just to say that these are disjoint. So i.e. these sets are disjoint. Okay, and here's the proof. So let a be an integer. The key to seeing that a is in one of these is just to use the division algorithm. So write a equals qn plus r. Q is the quotient, r is the remainder, where r is between 0 and n minus 1 inclusive by the division algorithm. Well, then a minus r is a multiple of n, right? i.e. n divides a minus r. So a is equivalent to r mod n, and thus the equivalence class of a is equal to the equivalence class of r by a proposition above. Okay, so that shows that every integer is in one of those sets. And so to see that these sets are disjoint, we'll consider R and S, where so the equivalence class of R and S, where 0 is less than or equal to r is less than s is less than or equal to n minus 1. And so r and s are one of these numbers, or two of these numbers between 0 and n minus 1. And let's say that they're different numbers. And we'll say that these, if they're different numbers, that these sets are disjoint. Then s minus r is, so we can say about s minus r that s minus r is bigger than 0, right? But it's also less than n, because s itself is less than n, so subtracting r can only make it smaller. And since r is strictly less than s, s minus r has to be greater than 0. Well, since s minus r is a natural number which is less than n can't divide s minus r, right? So n does not divide s minus r, i.e. s and r are not equivalent mod n. So the equivalence class, well, remember, s and r being equivalent mod n is equivalent to saying that their equivalence classes are the same. So that means that these equivalence classes are not the same, right? And if those equivalence classes aren't the same, then the only conclusion is that they're disjoint. Right? So by the first proposition above, Thus, their intersection is empty by the second proposition. Okay, so basically this proposition just says that there's a nice way to label all of the equivalence classes of the integers mod n. And you'll notice that we actually used particular properties of the integers here. So we use the division algorithm. So in general, when you have an equivalence relation on a set, there might not be a particularly canonical way to label the equivalence classes like we had here. All right, so what of this holds in general? And so basically we've seen with this with equivalence mod n that you can split the integers up into these n equivalence classes, and these equivalence classes are they're either disjoint, right? So you have two integers k and l. The equivalence classes of k and l, they're either disjoint or they're identical, and we can exactly say when they're identical. They're identical when k and l are related to mod n. When they're equivalent mod n. And we'll see that this is exactly the case in general, because we didn't use any of the properties of the definition of equivalence mod n in the proof. So we just used the properties of being related. So in general, we have a definition if R is an equivalence relation, on a set A, and A is in A, the equivalence class of A with respect to R is the set A in brackets. We just read that as equivalence class of A, and it's the set of X in A which are related to A. So it's the set of X such that X is related to A. So you have A in your set A. The equivalence class of A is all of the X that are pointing to A. All right, so this would be sort of the picture is that, I guess if the big blob is the whole set A, then this in here, this is the equivalence class of A. And then if you had like B over here, then the equivalence class of B would be all of the let's see, I already used X, Y, and Z, so I don't know, let's say X prime, Y prime, and Z prime. And so then you would have an equivalence class of B as well. So that's kind of the picture. And of course, in this picture, if you have any arrow pointing from something to A, then there's got to be one pointing back as well. And there's got to be, A itself has got to point to A. There's got to be an arrow there. And consequently, there's, all of the arrows connecting all of these things mutually. All right, so that's the picture. Okay, and we have the same propositions that we had for equivalence modulo n. So the first one tells us when, so this is actually the second proposition we proved before. I'll do them in reverse order because I think I like the flow of that better. So A intersect, the equivalence class of A intersect the equivalence class of B is is either empty or the two things are equal. The two equivalence classes are equal. Right? So you can't have any overlap of the equivalence classes unless it's equal, unless the two equivalence classes are entirely equal. Okay, so this is the dichotomy between equivalence classes. The proof is that if the equivalence class of A and the equivalence class of B, you notice this is going to be exactly the same proof that we did before. Just we're not going to be using mod n anymore. We're just going to be using the relation R. So if the intersection is not empty, then there's a C in the intersection, so that's in both of them. So there's a C that's in A and also in B. So thus C is related to A and C is related to B. And C is related to, let's see, right. So we'll just use C as our middleman, so we just have to switch this first one by symmetry. A is related to C, thus A is related to B by transitivity. So A related to B, well, thus, so in the case of the mod n, right, when K and L were equivalent mod n, the equivalence class of K and the equivalence class of L were equal. So we'll just have to prove the same proposition we proved then. So the equivalence class of A being equal to the equivalence class of B will follow from the next proposition. So from this proposition. So the proposition being that A is related to B if and only if the equivalence class of A equals the equivalence class of B. And so the proof is, so suppose A is related to B. Now first let C be given in the equivalence class of A, so that C is related to A. Well, what we want to say is that C is related to B, but we can do that by transitivity, right? C is related to A is related to B, so C is related to B by transitivity. By transitivity, C is related to B, i.e. C is in the equivalence class of B, and so the equivalence class of A is contained in the equivalence class of B. Now let D be given in the equivalence class of B arbitrarily. Then D is related to B by definition. And we still have A is related to B, so we just need to flip that one around. So by symmetry, symmetry applied to A related to B and then transitivity, and so if you apply symmetry to A related to B, you get B related to A, and then you'd have D related to B, B related to A, so D is related to A by transitivity. So D is related to A. Thus, D is in the equivalence class of A by definition. And the equivalence class of B is then contained in the equivalence class of A. So for the converse, it's the same proof that we gave before. Assume that the equivalence class of A equals the equivalence class of B. Well, we want to say that A is related to B, which is just to say that A is in the equivalence class of B. So we want to show that A is related to B, i.e. that A is in the equivalence class of B. But the equivalence class of A equals the equivalence class of B, right? And A is in the equivalence class of A clearly, since A is related to A by reflexivity. So A is in the equivalence class of A, and that's equal to the equivalence class of B. So A is in the equivalence class of B, and we're done. This completes the proof. Okay, so you see again, we use transitivity, symmetry, transitivity, and then reflexivity. So we used all of our properties there. And so A related to B is equivalent to equivalence class of A equals equivalence class of B. So in our first proposition here, where we got A is related to B, it then follows that the equivalence class of A equals the equivalence class of B. So again, we get the same basic features as with equivalence mod n for any equivalence relation on a set. So the corollary is that every element of a set A with an equivalence relation R is in one and only one equivalence class. And the proof is simple. So let A be in A. Then A is in the equivalence class of A, since A is related to A. Right? I mean, we already sort of said that in the previous proof. And to see that it's in only one, well, basically, if it were in any other, then that equivalence class would overlap with the equivalence class of A, and they would have to be exactly equal, right? Because they're not allowed to overlap non-trivially. So if A was in some other equivalence class, then the intersection of these two equivalence classes would be non-empty. So we'd have right. So all we've said is that if we take any equivalence class whatsoever that A is in, then that equivalence class has to be this one equivalence class here. So that's the only equivalence class that A could possibly be in, right? We started with this arbitrary equivalence class here that A was in and found out that that was equal to that particular one. So there's only the one equivalence class. Okay, so the basic picture that arises here is this one. So let's say this is your set A here. And so you take some element A in A, right? Then A is in its own equivalence class, right? So there's an equivalence class of A, which is all of the things that are related to A. So since there's a little arrow at A is in the equivalence class of A, and then there's a bunch of other things in the equivalence class of A. And so maybe let's say B is in the equivalence class of A, and C is in the equivalence class of A. And so we have these other arrows, and we have to have this arrow as well. And let's just keep the picture simple. We'll just keep it to that. So this is the equivalence class of A here. Okay, so the one proposition tells us that because A and C are related, right? A and B and C are all related. I could also equally call this the equivalence class of B and the equivalence class of C. And if we have some other element of A that's not in that equivalence class, so let's say we have D over here, well, D is in its own equivalence class, right? So D, there's an arrow pointing to D. There's also going to be other stuff, maybe. So we might have E and, whoops. E and F and maybe G. And so therefore there must be arrows between all of these guys. Right. Okay, and this, we call this the equivalence class of D. Oh, right, I realized I forgot the loops here, so there should be loops at C and B over here, and there's got to be loops at G and F and E as well. So you can call this the equivalence class of D, but you could equally well call it the equivalence class of E and the equivalence class of F and the equivalence class of G. Right. And maybe there's other things in this set as well. E, F, G. So maybe there's H over here, right? But anything in the set A must be in an equivalence class. And so H could be an equivalence class all of its own. Right? So this might be over here just the equivalence class of H. And let's say, so maybe our set A is just A, B, ... through H. And so this is what our equivalence relation does. It has to break up our set into these equivalence classes, and everything is in an equivalence class, and no two equivalence classes overlap. So basically the equivalence classes, equivalence classes break A up into disjoint pieces, and this is called a partition. It's called a partition of A. And I hinted at this last time, but we're much closer to the goal this time, and you hopefully have a more robust sense of what's going on and how equivalence relations sort of create this partition of your set. So what we'll cover next time, we don't have time right now. What we'll cover next time is the fundamental theorem of equivalence relations. is that equivalence relations always corresponds to partitions. And vice versa. So that's an informal way of saying it, but the basic idea is that if you have an equivalence relation on a set, that the picture looks just like this picture of our set A up here. For any element in your set, you look at all the things that are connected to that element. That's your equivalence class, and then that equivalence class, that's a subset of A. That's going to be one of the elements of your partition. So partition is just a bunch of subsets of A that are disjoint and cover the whole set. So you just look at all the different equivalence classes. That's going to create a partition, and conversely, if you have a partition of a set, so if you have your set A and it has a bunch of elements in it, and you have a partition, so your partition might break up your set into a bunch of pieces. Then the equivalence relation is just defined by saying that everything that's in a particular piece is they're all related to each other. So you can make your equivalence relation by saying, okay, this guy, these three elements in this piece are all going to be related to each other. And these three elements, they're all going to be related to each other. Right, and these two elements, they're going to be related to each other. And this element's going to be related to itself, and so on. For every piece, so for every subset that's in that partition, you just say that everything within that little subset is related, mutually related, and then that's going to define an equivalence relation. All right, so we'll cover that and more in the future.